Logic gates are the basis of computers and is also an interesting part of math. Today I'm going to explain all the different types of logic gates and how they work. So a few things you need to know before we move on to the different types of logic gates. So logic gate is based on binary, which is a number system that only uses 0 and 1. But you don't need to know too much about binary, because the only thing about binary that we're going to be using is just bits. So a bit is just basically a binary digit. It's a 0 or a 1. We will be using this as our inputs and outputs for our logic gates. So an input is basically a number that goes into a program. Then the program does something based on the input to give an output. Now we also need to know about something called a logic table. A logic table has some inputs and some outputs. In this case I have 2 inputs and 2 outputs. A logic gate will have either 1 or 2 inputs and only 1 output. This is not actually a logic gate, but 2 logic gates chained together. So the inputs are listed in order, normally as binary numbers. So these are just basically all the different combinations of the 2 inputs you can have here. Then here we have the outputs. So the outputs is what the program gives out, as I said before, and they are listed right next to the corresponding inputs. So here is just a first impression of all the 8 basic logic gates. Here I have the names and the symbols for the different logic gates. So this is a buffer, this is a NOT, this is an OR, this is a NOR, this is an AND, this is a NAND, this is XOR, and this is XNOR. Now I'll explain them all. So a buffer basically gives an output that is exactly the same as the input, so it does nothing. A NOT is the opposite. If its input is a 0, then it gives a 1. If its input is a 1, then it gives a 0. Normally we won't be using buffers because it doesn't actually do anything to change the input. An OR gets slightly more complicated. We have now 2 inputs. So an OR is exactly what its name says. So it only gives an output of 1 if the first input or the second input is a 1. So it's only a 0 if both the first input and the second input is a 0. Then we also have NOR, which again is the opposite of OR. So wherever the OR gives a 0, the NOR gives a 1, and wherever the OR gives a 1, the NOR gives a 0. Note that if you have an OR followed by a NOT, then you will get a NOR. So an AND, again, it's exactly what its name says. The output is only a 1 if the first input and the second input is a 1. And again, NAND is just going to be the opposite of AND. Wherever the AND gives a 0, the NAND gives a 1, and wherever the AND gives a 1, and the NAND gives a 0. And again, the NAND is also an AND followed by a NOT. Now, the final types of logic gates are XORs. So an XOR has a 1 if the first input or the second input has a 1, but not both. So XOR can also be called exclusive OR, and the 1 1 gives 0 is the exclusive part. Then we also have XNOR, which again is the opposite of XOR. Note that it's not N XOR, it's XNOR. We can actually also chain together logic gates, as I have said many times before. So chaining together logic gates is basically having some logic gates, then using some of the inputs as new outputs, or having the inputs be the same input for different logic gates. So in this case, we actually have 3 inputs and 1 output. So the AND first takes the A and B, the first 2 inputs, and then gives an output, and then this output is now used as an input for the next logic gate, the OR. And the other input for this logic gate would be C, and then we get the output. We can also split these signals. So if we have here, again, the first part is the same. So we have the first 2 inputs giving an output. Then the output is now given as an input for both the NOT and the OR. So in this case, we actually have 2 outputs. So that's it for this video. Thank you for watching. Hopefully you found this information interesting. I recommend you to continue exploring logic gates and see what useful functions you can make by chaining them together. And just as another reminder, here are all the logic gates again.